Label is a symbol that we're going to branch to, which is another instruction after this. So if these two are not equal, I'm going to skip. I get out of this condition. Suppose these two are equal, I'm going to go to the next instruction because I don't take the branch. What do? Then I add S0 and S1. Picture the bits flowing, okay? I add them, and the bits flow into S3, which is like register transfer notation. So question, why did I test the negative case here versus, because it says equals, right? So then why did I do not equals? You can do either way, but if you do equals, how would it look?
You need to put the add condition under the label?
Yes. So here, S0 branch equals. So S0 comma S1 to label. And here's my add. S3. Why S3? Because we want the output to go into H. That's dollars S3, dollars. What are we adding? I and J. S0, S1. Why am I S2? Oh. S0, S1. These get added and put into S3. But suppose, so this case is working, except what happens is, suppose that these two are not equal, we execute the next instruction. So you can see we're executing this if it's equal or if it's not equal. That's not what the programmer wanted. So this set of machine code does not match. Well, what's one way to fix it? What you can do is you can say jump here to past a label. So past label is another symbol I'm declaring with the colon here. And what are we going to do here? That's the next instruction. So how does this work using the positive logic, which matches this? So if S0 is equal to S1, I equals J, then go to label. Label's here. We add S0 and S1, which is I plus J, stored in S3, which is H. Good. What about the case where they're not equal? The case where they're not equal, we don't take the branch. If we don't take the branch, what do? We execute the next instruction, because what the processor does, executes this instruction, then the next, then the next. So this will skip over this. So you're going to say, well, why didn't I write this in the beginning?
Shorter.
Exactly. Instructions are time. Right, that's module 2. You guys are studying for the quiz. I made an announcement. Everybody get the announcement? I still see people don't have turn their announcements on. Turn your announcement on because there are good hints there. I don't want anybody missing out. I'll tell you what to study. I sometimes like even there's like little hints on the program or the project or like good things, some goodies. Okay, but as we know, right? If we talk about execution of instructions, each one takes time. It takes energy. So using the reverse logic. Here, we're using reverse logic. This statement only requires 2 instructions. Using the forward logic or positive logic, it actually takes 3 machine instructions. Okay, question.
So in that first one, after it does the whole adding thing, will it skip the label instructions on its own, or will it just?
No, it will execute label. So label will be maybe the next thing, like li dollars v0 comma 4. Because you want to print that integer. So this dot 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 is showing like the next instruction in the program.
If you get 2 terms, whatever, that are equal, so you don't jump to label, you do the add S3, S0, whatever.
Correct. Which is this.
Yeah, so then is the next step going to be label, or does it skip over label?
The next step is label. Because why? Because we always execute the next instruction unless it's a branch or a jump. Let me say it again. We're going to make a note in your notes. We always execute the next instruction unless it's a branch or a jump. So this was not a branch or a jump. So it must execute the next instruction. That's why this takes more code, because if we don't skip over the add, we're going to execute the add either way. because we just branched to label and we don't put a jump in between. If we didn't take the branch, which meant that they were not equal, we still added anyway. So we have to skip over this. It's another instruction. So here's putting an else clause. Without even looking at it, what do we do for else? We're going to have to have another jump, right? We have to skip over the else if we did the true part. Have a statement, if condition, then, and then clause 1, else execute clause 2. Every time we have a semicolon is a statement, means some action. So we call this the antecedent. Antecedent, if antecedent, then consequent. So the antecedent is a condition. Condition is some test of equality, greater than or less than, which we'll explain in the next slide. So if condition, one way to implement this is if condition is true, go to L1, which is clause 1. And then we go on to L2, which is the next instruction. If this condition was not true, instead of going to L1, it did not take the branch, it's going to execute the next instruction because the condition was not true, which is clause 2, which is the else. So if the condition is not true, we do the else. Then what? We have to skip over the then, consequent, which is a continuation to the next instruction in the program. Can we see this in MIPS? Okay, yes. So here, if I equals j, then what we did in the last slide, add together, else subtract. So here I'm actually testing the positive condition, the positive logic. If I equals to j, then branch to true. Okay, so under this true, better be the addition, right? Yes. The true case. But if I don't branch to true, I'm going to execute the next instruction, which means what? I'm in the else case, so I'm going to subtract, and I'm going to jump, because I'm in the false case, to the instruction after this whole statement is done. You can write this also as a flow chart. So a flow chart has a diamond for any decision box. We're seeing if I equals j. There's two choices. It is equal or it's not equal. If it's equal, we take this branch, we're going to add, and then if it's not equal, we're going to subtract, and then the flow of control, see the flow of control, remerges at this point for the next instruction. We're executing this statement. Another question, is this j that j? No. So we have to sometimes get it from context. So if this is assembly language, the assembly language has a format. The format is instruction opcode or operation, which is we call a mnemonic, and then the operands, either monadic, dyadic, so forth. So J has to be an instruction, not a data item. This J in the C program is a variable. This J, I'm sorry for the confusion, but this J is actually a type of instruction, which means jump. How do I know that it's not a variable? Because it's in the column for the opcode. Mars, you can see that they actually make all the opcodes to be blue, and then they make operands, if they're a register, it makes it red, a little bit clearer to see. So actually J is a jump. When we watched the video from the Scott CPU, he had compare instruction. We have different instruction classes. Some add numbers as arithmetic, right? Some compare bits as logical. So one way to compare bits is to set a register based on the relative value of two input operands. The semantics for SLT, which is set less than, if $S1 is less than S2, so you can just plug a less than symbol in between these and that's what it does. Then T0 becomes 1, which we use the word set. If I set a flip-flop, it means I load it with 1. If I reset a flip-flop, I load it with 0. Get used to these words, set and reset. As electrical engineers, we know when we set a value, it's going to the high voltage. If that's 1.2 volts, that wire is now 1.2. We've set that condition. If we reset, means make it 0 volts. So you're going to say, well, T0 gets set to either 1 or 0. There's 32 bits sitting there, so actually we're just turning on or off the least significant bit. 1 written as 32 bits, it's 31 zeros, and then the last bit is a 1. 0 written as 32 bits is 32 bits of 0. So this is what we call register mode of SLT. And this is immediate mode of SLT. Sometimes you want to compare to a constant. We can save an instruction sometimes. We don't have to load 7 into a register and then use that register. We can use it as a constant. And this 7 becomes part of the instruction, which is in this box. Remember we were adding 1, and that 1 was part of the instruction? We're going to see in this case for 7, it's not immediate. It's called register mode. It takes in 2 register operands, and the result goes to a register. If it's immediate mode, it takes in 1 register as an input, and the other number is a constant. 7 or 1, or we call it immediate because when we look inside the circuit and we design it, coming very soon, this value is immediately available. I don't have to go to the register and look it up. It's immediately available. It's always 7. So actually what this happens in immediate mode, this constant is encoded as part of the bits of the instruction. We can see that. Let's try a little example. Go to Mars. Let's make a new program, close, and a new. So let's ADDI. Oh, let's do what we're doing. SLT. SLTI, right? That's what it was. SLTI. And it can be anything. T0, S2. And because it's immediate mode, I have to type a number as a constant. 7. You have to save it before you can assemble it. So why is it not assembling here? Oh yeah, function. Function, I have to press this. There we go. So now this is assembled. It's just a 1 instruction program. But we can see the bit pattern here. See the last 16 bits? That's 4 hex digits, right? 16 bits. What is that number written in binary? The I wrote here. 0, 4 bits of 0, 4 bits of 0, 4 bits of 0, 1 bit of 0, and 3 bits of 1, which is 7. Why 7? Because the 7 got encoded as part of the instruction. If I change this to, good question, I change it to 25, what is the instruction, what's the last 16 bits of instruction going to become? Before I press assemble. 25. Now, first question, is 25 decimal? How people say it's decimal? Yes, and you're right. If we don't say any other units, it's always decimal in this class. So this is 25 decimal. What will it be? What will the bit pattern be down here? This was 7, right? So.
Would be one at the end of that voltage.
Okay, so I like it. This is 16.
And then 8.
And an 8 gives you to 24. 0, 0, 1. Totally. Let's take a look. So in hex, what is that in hex? This is 1. I'm sorry, it's getting like over here. 1. And what's this in hex? Yeah. Let's see if we got a 190019 as the last 4 hex digits. 0019. Okay. So now we're seeing, pretty cool, we're seeing the von Neumann stored program concept working. We've written an instruction, we stored it as bits. Yeah, you're going to say, what are these other bits? We're going to get there. Actually, it's almost as simple. Each register number has a number, and that's encoded as part of those other bits of the 2-8. We'll show you what the mapping is. We'll wait till the next module to do that. But we'll show you that. So now we're seeing the von Neumann store program concept. We're seeing what the processor executes, seeing what's in memory, seeing what the processor does. So here we see an example of using set less than. So symbol table, G has S0, H resides in register S1. We can set this if S0 is less than S1. T0 is not equal to go to label, which is going to be a skip condition. Maybe it's easier to see this. So suppose you want to do test for the less than, see this is greater than, test for the less than case, and then you know you're skipping it. So if you're saying here, if this is greater than or equal to 1, this is less than or equal to 1, T0 gets set, and I'm going to check if T0 equals 0, which means it was not less than, which means it was greater or equal.
Right. So
then do it. Do what? Branch to loop. How do you branch to loop? Well, if T0 is equal to 0 meant that this condition was not true, that this was less than, means it must have been greater or equal, therefore go to loop, which is what this said to do.
Is there a command for set more than?
No. There could be, if you designed it in the hardware. The people that designed MIPS only had set less than. Then we put a hardware for that. It turns out, which is the next slide, that you can actually do branch less than, branch greater than, like we're talking about greater than case. They're pseudo instructions, so the programmer can type it and Mars will translate it into a sequence of the corresponding set less than and branch, like we just saw in the previous example, to make the right semantics. But these are the intrinsic hardware, right? Functions is only set less, no greater, set less, and branch equal and not equal. Those are the only, there's only two branch, actually, in hardware, there's only two branch instructions. Branch equal, branch not equal. The only way of comparing is actually if one is less than the other. You're going to say, well, what if it's equal, which we saw, right? Test for the less than case. Then you know it's not true. Well, then it must have been greater than equal. Suppose you want to test if it's equal. Just use BEQ as test equal. So this is amazing, actually. MIPS processors, actually, everybody's phone has, if you have Android, has at least one MIPS processor in it. Anything we want to execute can be expressed as an equal or not equal condition. That's amazing. No matter how complicated the semantics is, the data is represented as bits ultimately, and what we do is compare a word at a time, after they're loaded into registers, to see if the condition is equal or not equal, and use some arrangement of those to convey the semantics that the programmer intended. Even if it's comparing, you know, do you live in Orlando? So maybe there's a list, right, of zip codes. You have an address, and you want to say, is that an Orlando address? Well, we see the pattern, right, is the 328 prefix, right? So I'm going to check the upper 4 decimal digits of the zip code. There may be different ways that that's stored in memory, but that actually comes down to equal or not equal condition on each of those. I have to test in succession, which is the next slide. So let's try a multiple test case. So the 3 has to match to be Orlando for the first digit of the zip code. The 2 has to match, and the 8 has to match for Metro Orlando. Well, how do you do that? We're testing multiple conditions. So here's some semantics that says if A is greater than B and this next condition is true also, then we set the flag as 1 as a yes condition. Else the flag is 0. So what we're doing is actually testing 2 conditions. How can we implement this as machine code? What does the hardware actually execute? It turns out there's no hardware on the planet that can execute this. I don't care if it's a Intel Core i7 model, 6, whatever right now is coming. It can't execute this. It's going to break it down into branch equal and not equal instructions in a sequence. Let's see that sequence. So the symbol table mapping is flag contains the bits in S0, and ABC are 1, 2, 3. ABC 1, 2, 3. Flag is S0. Okay. So the first solution is using intrinsic instructions actually provided by the hardware. So here's set less than. The first thing I'm going to do is compare. This is A, B. So B less than A. Then T0 gets set. If B is greater than, that means if this is the only condition that sets it, it resets it otherwise. So it's reset if B is greater than or equal to A. So we wanted A greater than B. But what we got is greater than or equal, it's T0. So next thing we have to check, if this T0 is equal to 0, which meant that this condition is true, which is greater than or equal to A, go to else. Okay, so what is else? Else means that we don't want to execute flag equals 1, we're going to set flag to 0. See, A greater than B, flag equals 0. A greater than B, flag equals 0. So here, if B greater than or equal to A, then T0 gets set to 0. So that's the case here. Well, what else do we have to test next? The C condition. If S1, which is A, is less than S3, which is C, A less than C, this gets set to 1, otherwise it gets set to 0. Well, this is actually handy this time because this A greater than or equal to C is what we want to check for. One way to check if A is greater than or equal to C is to set less than A comma C. If it sets less than, and then to test what? Then we look for the 0 condition rather than the 1 condition. So we branch not equal to else. If this is not 0, then it meant that the condition is not true. So both conditions, so what this means, we execute one instruction after another unless we take a branch. So the only way to get to this statement is if both conditions are met. If both conditions are met is the only way to set S0 to 1. Why is it set S0 to 1? Add immediate, a constant value of 1 to 0 means the answer is 1. Those bits get stored in S0. We set S0 to 1. S0 was flag. So we set flag equals to 1 if both conditions are met, which is what we said we wanted to do. Else, we jump over the setting to 0, right? After we did that, we jump. So if we got to this statement, it meant that one or both of the conditions were not met, you set the flag to 0. This looks like we check both of these conditions, but actually, if it's an AND condition, we say AND is 0 sensitive. I put a 0 into an AND gate, doesn't matter what the other inputs are, the output's 0. So if I see here that this condition is not met, I can set the flag equal to 0 immediately without checking the other one. This is a common thing to do in a circuit design class. Maybe you even had this question, right? I don't know. Here's AND gate. And we have a whole bunch of gates over here and some XORs. And an OR, and a whole bunch of gates over here. And then we have an AND gate at the end. What's F? 0. Do you need to calculate anything? This is a great final exam question, right? Because if you know what AND gate is, you know you don't have to look at any of their inputs. F has got to be 0 because we say, this is a little takeaway that you can write in your notes, AND is 0 sensitive. What's that mean? It's sensitive to the 0, any input of 0, sensitive, makes the output to be 0. OR is 1 sensitive. Any time you get a 1, any input is a 1, the output's going to be 1 no matter what the other inputs are. So AND is 0 sensitive, OR is 1 sensitive. What that means is if I get a negative output here, if one of these conditions is not true, do I have to check the whole long string going forward? No. No. If this is not, if one of these, the first time I get one that's not true, just stop checking. Well, it turns out that's what the processor does. You see? Once it finds one of these conditions is not true, you went to else and you're done. Did they check the other ones? No. Do you need to? No. Because once you get one that's not true, it said that that both had to be true. You can stop.
Is it always in that order that it checks it? Like the order that's written? Or is it just...
It's up to whatever the programmer writes or the compiler translates. So when we look at here, for sure it's in order. That's one instruction after the next, unless the branch is taken. But you can do it in different orders. All right? I could write this testing this condition first. It will still work. If that second condition is not true, then I don't bother to check the first condition. But to get to the line of code that actually sets it to 1, they both have to be true. That's the only thing that matters. You can check in either order, as long as they're both true is the only condition that allows you to set that variable. Here's our last slide for today. Take some C code. Let's map this to assembly. Getting a little more realistic here. Turns out each one of these structures has a corresponding representation. So the green box is initialization, yellow is the main code, this is input or output, and this is exit. There's a clean exit from the program. So this is initialization, and I is initialized to 1. How do you initialize I? Well, if I is in T0, which is given, it's probably written up here somewhere in the problem, but we're just saying it right here. X is contained in T1, so if I load immediate value of 5 is a constant, immediate 5 into T1, that's the same as initializing X equals 5. What about this loop? How does this loop work? Well, in C, this is saying if I is initialized to 1, every time we have a semicolon, it's actually a statement. You're going to say, well, they say it's a for statement. Well, for statement has multiple statements inside of it. So the first statement is initializing I to 1, and then setting I less than or equal to 3 as a test condition that we either meet it or not. We keep inside the loop, incrementing I each time we complete this loop, which is the brackets. What do we do inside the loop? We add 3 to X, and we subtract X from Y. So here you can see that happening inside the loop. We add 3 to X. X is in T1. Add 3. Here we subtract X. See the X? T1. After we compute T1, which is X, we subtract it from Y. Put the result in Y. We're done, except what? Every statement has to have at least one instruction. So here this instruction is adding 1 to T0 means increment I. Because I was T0, is incrementing it, adding 1 to it. What do? We branch back up to loop. See the label? This is labeling this instruction, which is stored in that address because of von Neumann's store program concept. We can see the bits. We did that today. We branch back up there if T0 is less than or equal, I use a BLE, less than or equal to 3. What about printing? Printing the console, we have to use syscall. So we look at the table, this is output in an integer. And with the integer print has to be an A0, so I have to move that into A0 and syscall. And then to exit, return code 0 means no error. And we do that over here by using syscall of 10, service code 10. Yeah, good.
Why are we loading 10 to V0 and on the other one to V0?
That's what I said.
Where? Oh, service codes. This prints an integer. This exits a program. It's the operating system call. When you call the syscall, it looks inside V0 to figure out what function you want to perform. If it's a 1, print integer. If it's 10, means exit. Okay, so that's enough for today. You guys are going to, what we're going to do is pick up where we left off last time. We're going to talk about another set of instruction classes, which is the load store, which is data transfer. So we've talked about 2 other instruction classes so far. Anybody want to take a chance to test our skills? We covered add, subtract, and that was different instruction class or category, which was what?
Branch equal.
Branch is another one. So branch is a control flow.
Right.
And then add, subtract.
Less than.
Jump.
Jump is control flow, but there's another class, category. Set less than's control flow. It's like compare, but arithmetic. Arithmetic logic is ALU. And one other major category is called data transfer, which is, we're going to go in more detail today. See several examples. Data transfer, the two instructions we use are load and store on MIPS. And we can select load word, store word. That's the size of the data transfer. So good review in MIPS. A word is how many bits?
8.
Okay. Any other votes? Any other? MIPS.
4 bytes is 32. It's 8.
Or 32 bits.
32 bits. And how many? A byte was your head. What's a byte? There's 4 bytes per word, but a byte is 8. I'm sorry, I should tell you what I'm asking you. 8 bits. 8 bits per byte, which means we have 4 bytes per word in MIPS. We're going to use that information today because we're going to use this byte addressable memory and look at providing an address on the address bus from the processor to the memory module. Look at how that actually is referenced by the memory to return the data back. The question is how much data. If we use a load word instruction, which is one variety of load, 32 bits gets returned. Why? Because in MIPS, each word's 32 bits. We're going to see in another slide, there's something called load byte. Load byte means I transfer a byte. They actually use lowercase b, sorry, but that's how they did it. That means 8 bits is transferred back from the memory to the processor. So that's what we're going to look at today. So start with load word. We have the mnemonic LW. It's also an acronym. And I think I mentioned all this. The key thing to keep in mind that's a little possible source of confusion is we're just copying the value over. It's like if you copy a file in 2 folders in Microsoft Windows, we're not moving the file, we're just copying the data. So the bits are copied over. Store word is going the other way. That's going from the CPU into the memory module. So we mentioned these here, the word size, and either bits is 32 or in bytes is 4. That's going to become very crucial. It's 1 hour of our lesson today, more or less. So let's look at inside the memory component or the memory module. We have a structure called memory map. Memory map is a very common thing to see if you're working with an embedded system or you're designing a system. Sometimes the compiler people tell us that these are the addresses where certain data has to reside. For example, in this memory map that's listed here, the machine code, which we call the .text segment, is in this range of addresses, and the source code is here. So let's relate these back to make it real, right? Let's relate this back to what we covered in the last class when we used Mars. We showed you Mars, you do it in the lab as well. Which of the windows would be the source code and which would be the machine code after we did the assemble, right? We had assemble and we had, in one window we had whatever we typed, ADDI, T0, such and such. And then remember last class we had some number over here and it was 0x, 03, whatever it was, right? 5, it was some hexadecimal number. This is the human readable, it's the source code. In assembly, right? This is source code in C, okay. But this is source code, and this is after it's been changed to the native format and the bit sequence that the processor wants to use. So that's what's called, we said, the machine code. And this was source in the Mars Windows. So here's the source code in C, and there's a C compiler. That's actually operating system type program. That's a system utility. Also in here, when we call syscall, is some routine, operating system routine. It has a starting address. So when you call syscall, actually what you're doing is you're running some code that's already residing in memory. It's that simple. We'll show you some examples. This is the machine code for your program, so that would be the code segment. We have different words for these. Each one of these is called segments. The point is that there's some map for memory. The first thing you have to know about memory map is where's the lowest address and where's the highest address. Sometimes we write 0 at the bottom of the screen or bottom of the page. Sometimes it's at the top. So it's just like when somebody hands you a map or you Google something, where's north, right? Sometimes they put north on the bottom or whatever, right? Depends on what perspective. So here, 0 is the lowest address. You always need to get your bearings on that. So whenever someone gives you a memory map, the first thing you look at, where's 0? So these are addresses going up, actually. So this is address 0, address 4. These are the byte addresses. This is what's used by load word and store word. So let's try some examples. To use load word and store word is the only way we can get data in and out of a processor back and forth to memory. And that's important because a lot of structures we use have to reside in memory. So if I have an integer array declared in C or any programming language, MATLAB, or it's Microsoft Excel column, it's a database in SQL. So it's a table, right? So where is that data stored? It has to reside in memory because inside the processor we only have 32 registers. We can't store the whole table or a whole data structure like 1,000 integers inside the processor. So we have to keep loading back and forth one entry at a time from memory to the processor. Each time we do that, we're going to process it, perform the operation, and then store it back to memory. We're going to store it back to memory if we have to update the value of the array. If it's just a temporary value, we can keep it inside a register. Suppose we're adding up a list. You only care about the sum. When you're done, you don't need the intermediate additions. You don't have to store out every immediate addition. But any value that we want to pass on to another part of the execution of the program, like another subroutine or another core. Right now we're only using a single core, but you may have multiple cores that communicate, and we'll talk about that. So here's a nice takeaway. This provides, I think, a pretty good perspective. Every time we execute a load or store instruction, it's actually overhead. So if you work at Google data center, so I watch that video to provide that perspective, and they want to cut their energy budget, and they're going to give you a vacation to Fiji, okay, for 2 weeks. If you can cut so much off, where's the first place you may look to make easy cuts in this machine code? Well, if you can get rid of load store, those are easy ones to get rid of if it's valid to do so, because actually they're not doing any computation. Why is load and store not what we say functional statements? Why are they not computing anything? Because they're not changing any bits. Computation is saying that the input and output has to be different, otherwise you don't need to run the machine, right? You already have the answer. If the output and the input are the same, if it doesn't change, you don't need to run it. Actually, that's a big power savings, right? So when we're in this class, load and store's overhead. Now here's something kind of interesting. You go to computer networks, that's the main point. Why?
Because on networks you're communicating from computer to computer.
And you don't want to change bits.
Right.
If you change bits, that's an error.
Exactly.
You drop some bits, right? So that's a transmission error. Well, they're both computer courses, but the objectives are totally opposite. So in this room, we want to minimize load store transfers because they're pure overhead. Computer networks, that's the whole point. So keep that perspective. We're going to show you how to load and store back and forth to memory. So here's the machine code, prototype load instruction, the semantics of load and store. This is the destination register. To take the address that's in S3, S3 is like a pointer. So the value that's in S3 is actually an address, and it's going to be added to the value that's outside it, which is 4, which we call the offset. So this is the base and the offset. Base is added to offset as unsigned integers, and then that becomes the effective address. The best way to, there's a number of bytes and bits that this can address, we'll talk about that. The best way to explain it is to show you an example. So here's LWT1 $8 S3. So what this means is look inside register S3. This is a processor. These are registers, so we're inside what unit here? Register file, right? Inside the register file there's 32 registers. Each register has a name. T0, S0. I just made this up, but there's S3. S3 has this number, binary hex. What is it? Hex. So this is a number in hex. That's an address. Why? Because we're going to take S3, we're going to add 8 to it. What does that look like? S3 contains this number. Here's memory. So what flows over the address bus? This number plus 8. So the processor says, I want to access this address plus 8. We look at memory. Memory is byte addressable. Each one of these is a byte. We see 4 bytes per word because, as we mentioned, MIPS has 32 bits is the size of its data word. It's not a 64-bit processor, it's 32 bits. Believe me, it's more than enough to get started. Especially you go to embedded system, you go back even to 8 bits because you have to put probes on each one of these bus wires to look at the data bits and so forth and the address bits. Like I said, we get working with 8-bit, 16-bit, 32-bit in this case, then you expand your word width once that's debugged. So here we wanted to go 8 bytes forward from this address, 1001 zeros. So this is 1, 2, 3, 4, 5, 6, 7, 8 is the starting address for the next 32 bits that's going to be transferred. How many bytes are transferred? 4. Here we see those 4 bytes. That's one word. Why was one word transferred? Because we use LW rather than LB. LW is load word. LB is load byte. Good question. When would you want to use one versus the other? Well, if we want to access an integer, integer is always stored as a word. Okay, integer stored as 32 bits. If I want to access a character, we mentioned before, a byte is about a character of text. How many distinct values can I represent in a byte? 2 to the 8th, 256. If I have a 32-bit number, how many values can I represent as a decimal value? We'll take your good advice.
Yeah. Thank you.
Is it about 4 billion?
It is exactly 4 gig when the gig is 1024 times 1024 times 1024. Because it's 2 to the 30 times 2 to the 2 is 2 to the 32, and that's 4 gig. Because 2 to the 30 is a gig, 2 to 2 is 4. So you can represent, if it's an unsigned integer, between 0 and 2 to the 32 minus 1. That's a pretty decent number. We call it an int. If you want a larger representation, you do long int, and they're going to give you 64 bits. But on most machines, an int is 32 bits. That's great because MIPS is a 32-bit machine. So we want to do a load word operation. There's an integer stored. You can imagine there's an integer stored here, but you're going to say, how is it stored? I see 4 bytes here. Which is the most significant? Good question. So the convention is that this is the least significant of the 4 bytes. So inside this box is a byte value between what? 0 and 255. And another value between 0 and 255. It's a number, right? That's a decimal number. But we can write it as binary, 1001, 100001110. There's 8 bits, it's a byte. And then another 8 bits. Okay. Going down, how are these bits transferred? This byte, then this byte, then this byte. Where do they go? Good question. That comes over to this least significant byte here. Why is that? Because we want to represent a number. This is the 31st bit place. This is a 0-bit place. Why? Because MIPS is 32-bit word. Can you see those bits? Yeah, we're going to actually look at it. You're going to see it. We drew a diagram, but we'll actually look at a real chip and we'll show you how to design these. What's inside? This is a register, right? What's inside a register? What physical? See, if you're a computer scientist, this is a number to you, and you look at that, and you know what it is, and you're happy, and you do whatever you do. You go to dinner, or go to the beach, or that's it. But we want to see what's inside. How does this work, right? Because that's why we're here. Because we want to build it because it's interesting to us, right? What's inside this is a register, 32 bits. What's inside here? Flip-flops. So if we look inside, there's 32 D flip-flops. We had a slide for that. We'll just pull it up again and refresh your memory, so to speak. I zoomed by it. There we go. So that's the contents of the register. Each one of those bits is stored in a flip-flop. You're going to say, okay. So, except for which register of these 32? This is the MIPS register file. Register 0. As we mentioned last time, we're just going to ground out each one of those because that's 0 volts. Remember, every information representation we use as electrical computer engineers is always a voltage. If we're doing digital, it's easy. It's either 0 or 1.2 or 5 volts is the upper voltage. It's either one of those two values. If you're working with analog signals, frequency modulation, well, that can be continuous signal. Then maybe we care about the spectrum and you do Fourier and we can look at different signal representations, but it's always a voltage. It's always a voltage on a wire. You have to get a voltage, you have to be able to drive some current, but we use the magnitude of the voltage in almost all the cases to represent information. Here we just represent a 1 or a 0, so it's either the high voltage or the low voltage. But I want you to have that view. Now we're going to be talking about moving data back and forth. You should understand it from the computer science point of view, but you should also understand this means we have signals to drive. There is inductance, capacitance. We're not going to make it that complicated yet, but in your future courses you will. When you design a real system, you have to worry about those because that's energy. That's why the chip gets hot. Okay? So we're moving data back and forth. We know those are bits, but bits are voltages traveling through some wire. That's not a perfect wire. It's not made of gold. Okay? They might have gold contacts at the end. Gold is our best known conductor, right? But copper's not too bad. Aluminum, not that bad, and that's what we use as these wire traces. So anyway, there is some resistance. We want to keep that in mind. So that's why it's overhead. It's costing energy. But we're moving data from here to there. Why you say, well, why didn't we just put this inside this box? Good question. We're going to see in a later module processor design with a certain technology to make those flip-flops fast.